For today's geometry notes, you will need in class 44. We are going to be talking about how to determine whether triangles are similar. So this is specifically triangle focused, and instead of being told at the beginning of a problem that triangles are similar, you're going to be deciding and justifying why two triangles are similar to one another. So just as a recap from our previous work with similar polygons, similar triangles are polygons, so they have the same characteristics. They are specifically going to have three pairs of congruent corresponding angles. Remember, the angles stay congruent when we dilate shapes, but then they will also need to have three pairs of proportional corresponding sides. Remember, those sides grow or shrink according to the enlargement or the reduction that happens. So if we think through those two scenarios, we are looking for a lot of information based on that definition. We would need to know a lot of information about angles. Three pairs means 6 different angles, and then same thing with sides, 6 different sides. So just like with congruent triangles, there are some shortcuts or some criteria that we can use that reduce the amount of information required, because if we meet those minimum expectations, then it forces all of the other angles and sides to have the characteristics that they're required to have. So the first one of these is going to be called angle-angle similarity. Angle-angle similarity. So when we look at angle-angle similarity, we're focusing on this first criteria here. We need similar triangles to have 3 pairs of congruent corresponding angles. You might be saying, well, that says 3, and we only use 2. The reason for that is if we know, for example, that this angle corresponds to this one pair of congruent corresponding angles, and then we notice that this top angle is used in both the small triangle and the big triangle. In other words, it's a shared angle. So we mark that it's congruent to itself. That's an old friend, the reflexive property, coming back to help us. Then what happens once we get those 2 sets of congruent corresponding angles is that if we were to remember our triangles added up to be 180 degrees, there would be no other option but for that third set of angles to be congruent to one another. That's actually a theorem called the third angles theorem that we don't necessarily need a name for, but that idea is that once we get to 2 sets of congruent angles, the third one just automatically happens. So 2 sets of congruent angles is enough to show that we have similar triangles. Okay? If those angles that correspond are congruent, it basically forces the sides to be proportional. So we don't need information about the sides. We can trust that because those angles are congruent to the angles in the other shape, the proportional sides will occur. All right, our second option when we're looking for similar triangles and we want to look at less information than the official definition is called side-side-side similarity. Now that similarity squiggle is important because we already have side-side-side elsewhere proving that triangles are congruent. This is different. Our goal this time is to prove that these triangles are similar, which means we're not showing that the corresponding sides are congruent. We are showing that they are proportional. So in order to use side-side-side, you would need something like this. So this is not information you would make up. This is information that would already be on your diagram. So let's say that we had sides labeled on this smaller triangle of 4, 10, and 12, and then we had sides labeled on this bigger triangle of 6, 15, and 18. Again, that would be given information to you. You don't make that up. It would be given to you as part of the problem. What you need to do then is you need to show that we have 3 sets of proportional sides, which looks like 3 ratios that are equal to one another. The way you set up your ratios is important because in order for these ratios to be equal, they need to be comparing corresponding sides, which means you want to find the smallest side and match it with the smallest side in the other shape. So I'm going to match 4 with 6. Then I'm going to come back for the medium side here. 10 is in between 4 and 12. 15 is between 6 and 18. So 10 would correspond to 15 as our medium sides. And then last but not least, back to this triangle, that's our longest side, and it would need to correspond with the longest side here. And then you check. You make sure that these are all equivalent and would provide you with the same scale factor. So if we simplified this fraction, both of those divided by 2 would give you 2/3. Both of these divided by 5 would give you 2/3, and both of these divided by 6 would give you 2/3. So since they all reduce to be the same value, that means that they're all proportional, and we know the scale factor. We could have just as easily compared the larger triangle to the smaller. All of these fractions would flip upside down, and the scale factor would have been reported as 3/2. That's perfectly fine. But that's the work required to show that you're dealing with similar triangles thanks to side-side-side similarity. You need the 3 ratios, and you need to show what they equal. All right, our third and final option is side-angle-side similarity. So this is a mixture of congruent and proportional information. The angle needs to be congruent, so you would need some kind of information about congruent angles. They could just be marked in your diagram, or they might be like vertical angles in the picture. They might be a reflexive angle in the picture. So all kinds of different options for how you would be given or be able to determine you have congruent angles. And then again, you would be provided with some information about the sides. So let's say that we knew this side was 10.5 and this side was 14. This one's going to be 8, that one's going to be 6. So for these two S's, you would need to do the same thing that you did over here, except we're going to show that there are 2 ratios of sides that are equal instead of 3. Again, we're going to match in a very similar way. So we're going to go for the smallest side, matched up with the smallest side, and then the larger side, back in that first triangle, matched up with the larger side. The goal is to show that these are the same. Now, when you have decimals inside fractions, it's a little bit tricky, so if you need help using a calculator to figure out what that's equal to, you should be able to determine that these both simplify to be 7/4. That's easier to see here, both of these divided by 2, but there are ways to use your calculator to help you simplify fractions that have decimals in the numerator or denominator. So that would be our scale factor. Because those both turned out to be the same, we know we have 2 sets of proportional sides, so that plus this angle that's between those sides tells us we're dealing with side-angle-side similarity. Okay. The rest of our time on In-Class-44 is going to be practicing those ideas to see if we can identify whether or not triangles are similar. We need to show our work. We're going to circle yes or no, and if we circle yes, we're going to say which of those 3 similarity criteria we're noticing. So taking a look at example A here, I don't have any information about sides, so that means that side-side-side similarity is out and side-angle-side similarity is out, which leaves just angle-angle similarity as an option. I see 1 set of right angles that would be congruent thanks to right angles theorem, and then 1 set of angles that are marked as congruent with those little circles. So this is a yes. These 2 triangles are similar by angle-angle similarity. Moving to example B, I don't see any angles given or able to be identified, so that means that both of these shortcuts that have A in them are going to be out. I do notice that I have all 6 sides labeled, so that means I'm going to test to see whether side-side-side similarity explains that these triangles are similar to each other. If I'm looking at this triangle to start with, I'm going to move from the left to the right each time. The smallest side is 2.8. That would correspond with the smallest side over here, 5.6. Back to the first triangle, medium side is 3.5. Longest or medium side over here is 7. And then back to the beginning, longest side is 4. Longest side is 8. So the goal is to investigate these fractions and see if they're really all the same scale factor. 2.8 over 5.6 is 1/2. 3.5 over 7 is also 1/2. And 4 over 8 is also 1/2. So our scale factor would be 1/2. That means all three sets of side ratios are proportional. So we can say, yes, these triangles are similar by side-side-side similarity. Moving on to the last two examples on this side of the page. We don't have any side information. So again, we can eliminate side-side-side and side-angle-side similarities in our mind, which means we're just looking for angle-angle. There is one set of angles marked on the page, but then I'm remembering anytime we have this x, those angles across from each other in the x are going to be vertical angles. So with a little bit of help from our vertical angles theorem, right there in the middle, we now, yes, have two pairs of angles that are congruent, so these triangles are similar by angle-angle similarity. Moving to example D, I'm noticing that I have number measurements for angles, and I have a 57 and a 57. So that's one pair of congruent angles so far. These other angles don't match, but since I have 2 out of the 3 in a triangle, we should fill in those missing angles to see what they're equal to. That will help us to make the correct decisions about whether or not these triangles are similar by angle-angle. So if we do 180 minus these two values, this angle is going to turn out to be 70 degrees. That's technically enough to notice that we're not going to have a match, but to be safe, you can do the same thing over here. Subtract 60 and 57 from 180 to fill that third angle in as 63. Sure enough, we only have one set of matching angles. None of the other angles correspond and are congruent. So this is our first no for today. Those triangles are not similar because we do not have any of our criteria met. Okay, so then just a note to make sure that this is on your radar and you won't forget, if you are using side-angle-side similarity or side-side-side similarity, you have to have those ratios. Or another way to think about it is you have to have those fractions on your page to show that you're testing for proportional sides. So this work needs to be there. If you're dealing with side-side-side, it'll be 3 fractions and then showing what it equals if there's a consistent scale factor, or if it's side-angle-side, it'll be 2 fractions. All right, go ahead and turn the page and meet me back here for a few more examples as we finish out these notes for today. We are going to continue on the back with 7 more examples. These are a little bit more complicated in some cases, and they add an additional thing for us to do. So if we say yes, they are similar, we're still going to be giving the reason why out of these 3 options, but we're also going to create the similarity statement. That similarity statement is where we have to match up the letters in the triangle name to show all of the corresponding parts. All right, taking a look at this first one, it looks pretty similar to that one we just ended with, where we can see one set of matching angles, but then we have 2 numbers that don't match and 2 empty angles. So taking time to subtract from 180, 180 minus 63 minus 21 will help us to fill in this angle here as 96 degrees, and that is enough for us to notice that we now have a second set of matching angles. So these are congruent by angle-angle similarity. You are able to name the first triangle whatever you wish. So you could name the top triangle however you wish, or the bottom. I'm going to name the top triangle, as triangle DEF. And then we want to correspond when we name the second one. So D was that 96 degree angle. That's going to match up with G. E was the 63 degree angle, so that matches with R. And then I didn't fill in angle F, but if I had, it would have been 21 degrees, and it would match with angle H. Moving along here, example B, we're real short on information. No sides marked, no angles marked, but 2 little arrow flags. Think back in your mind to first semester. That means those sides are parallel. So when we had parallels, we could look for corresponding or alternate interior or alternate exterior angles. Those were the three angle pairs that would be congruent. So if we're looking at angle R, we can follow that transversal to find an alternate interior angle out here at T. Or we could look at angle S, follow that transversal to find another alternate interior angle out there at G. So alternate interior angles theorem helps us to say, yes, these are similar by angle-angle similarity. We also could have used vertical angles theorem to help us instead of using alternate interior angles theorem twice. Again, we can name that first triangle whatever we wish. So I'm going to do triangle SQR. S corresponds to G. Q is the vertical angle, so it would correspond with Q on the other side, and then R corresponds to T. Moving ahead to example C, again, very, very little information on this picture, but we are dealing with a situation where we have a small triangle within a large triangle. Anytime that happens, there's going to be a shared angle that we can mark as being congruent to itself using reflexive property. First semester, we used reflexive property very often, but almost always dealing with sides. Now we're using it to deal with angle T being shared by both of these triangles. But I think that's it. There's no other angles marked. There's no other side lengths for me to be able to test proportions. So we are short on information. We do not have enough to show that those two triangles are similar. Example D, no angle information, but all kinds of side lengths. So I'm going to start setting up some ratios here with the intent to either show that they are equal or not equal to make my decision. I'm going to move from the top to the bottom each time. So in that top triangle, the smallest side is 4. In the bottom triangle, the smallest is 4.8. In the top triangle, the medium side is 5.5. The medium side here is 6.6. And then back to the top one more time, longest side 8.25, and longest side here is 10. Now those ratios for sure are ratios where your calculator is going to help you to determine whether or not they're equal. So if I plug that in, 4 over 4.8 is just 4 divided by 4.8. Your calculator might display a decimal. There should be a button on your calculator somewhere where you can change decimals into fractions. Again, if you're not sure where that is, ask your teacher for help. So that ratio right there is actually equal to 5/6. If we type the next one in and we do the same thing, it's also 5/6, and then one more time, 8.25 divided by 10 is not 5/6. 33 over 40 is the fraction that I'm giving there. So these are not all equal. If they are not all equal, that means we do not have 3 pairs of proportional sides. So this is another case where our triangles are not going to be similar. So just because the sides are labeled doesn't mean that you're smooth sailing. You really have to test all 3 of those fractions. 2 worked, but the third did not. So those triangles are not similar to one another. All right, moving ahead to example E, I'm noticing some interesting things happening here. Congruent sides are a little curious because our goal is not congruent sides. Our goal is congruent angles or proportional sides. But since these sides are in the same triangle, that means we're really dealing with those isosceles triangles back from first semester. And then we've got our base angles theorem that tells us if those 2 sides match, so do these 2 angles. So even though I'm not noticing any matching angles right now between these 2 triangles, I could use that fact to subtract 26 from 180. And then because angle B and angle D need to be congruent, I can split up those leftover degrees between those 2 angles. And it does turn out then that those two angles are 77. If I think about that same idea in this triangle, across from these congruent sides would also be congruent. I'm noticing that one of those angles is 77, so I can grab that and move it into the other corner. So we do have two pairs of congruent corresponding angles. So those sides aren't really sides that are going to allow us to use side-side-side similarity or side-angle-side similarity, but they do give us some clues for how we can fill in our angles to notice angle-angle similarity. Now, there are two different ways you can write this similarity statement. So if we start over in this triangle, I'm going to call this triangle BCD. Angle B is 77, so it could correspond to R or T. Angle C is not 77, so it has to correspond to S. But then D could have corresponded to R or T. Since I already used R, I'm going to use T. But it would be perfectly acceptable for you to also have written TSR as the name of that triangle. Since those two angles match, you can flip your R and your T and still have a correct correspondence. All right, two more examples. I am noticing those flags again for parallel lines. So we're going to follow those transversals. We're going to have some alternate interior angles there, thanks to that top parallel and bottom parallel. If we switch over to these parallels, we're going to have more angles in those same two corners that are alternate interiors. So using that alternate interior angles theorem twice is going to give us a yes for this based on angle-angle similarity. I'm going to name the top triangle first, so that would be triangle EFG. E has my double mark attached to the side parallel, so that's going to start with a G in my other triangle. F is the empty angle, so that corresponds to H, and then G is marked with the single arc. That's going to correspond to E. Now, if you're thinking, wait a minute, shouldn't we be marking reflexive property there? Yep, we could actually show that these two triangles are congruent, which brings up a good question. Are congruent triangles similar? The answer is yes. The scale factor for congruent triangles is just 1. So it's kind of weird to think about congruent triangles as being a dilation, but it would be a dilation just using a scale factor of 1. All right, last example for today, example G. I'm noticing right away I've got some vertical angles, so I'm going to use that vertical angles theorem to mark a pair of angles there in the middle. And then I've got some sides. So I'm thinking about investigating a little side angle side similarity here with two ratios. I'm going to move from the left to the right. So the shortest side, 4, would match with the shortest side here, which is 12. Longer side here, 15, would need to correspond to the longer side here, 15. Those two, I think, are both equal to 1/3. Dividing both by 4, dividing both by 5, so our scale factor would be 1/3. If those two sides are proportional and we've got the angles in between them, this is a yes by side angle side similarity. All right, one last similarity statement to write, and then we're done. That triangle on the left, I'm going to give the name triangle KLN. KL was the longer of the two sides, so it would need to match with the longer of the two sides here, keeping in mind that angle L corresponds as well. So KL will match with HL, and then out along the small side would send me out along the small side to finish at Y. All right, everybody, that's it for in class 44. Thanks for watching. We will see you back in class.